Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. In 2018, physicists made an unusual discovery. For years, they'd been playing around with graphene, a single atomic layer of carbon with promising electronic and mechanical properties. But they found something even more surprising when they laid down a second layer of carbon atoms on top of it at a slightly twisted angle of 1.1 degrees. Physicist Mihir Pendarkar of Stanford University tells the story.
When they cooled this material down with graphene at very small angle, it became superconducting. And that's very shocking. We didn't expect superconductivity there. It made everybody rethink, do we really understand superconductivity?
Since then, physicists have been studying what they now call twisted bilayer graphene to better understand its electronic properties. These properties include unexpected magnetic states of matter, along with the superconductivity. The two layers create a new periodic structure in the material known as a moiré superlattice, corresponding to a periodic potential.
The electron now sees this new periodic potential, and it actually behaves as if it is not in just that one layer of graphene. It behaves as if it's in a brand new material.
Researchers are also studying other atomically thin materials other than just carbon. Eventually, these materials might enable new types of electronic devices, although currently researchers are working to understand the basic science. But they've given this new field a name, twistronics. But understanding the odd electronic properties of twistronic materials has been difficult, because it's hard to reproduce the materials themselves. Slight changes in twist angle of the two layers, even hundredths of a degree, can result in the material having dramatically different electronic properties.
I'll let you in on a big secret, or maybe an open secret that everybody in this field knows. We cannot make reproducible, repeatable samples in this field.
In many cases, there exists only one sample of some particular twist angle or property. On top of that, another problem is that it currently takes weeks, even months, for researchers to measure and confirm that they've created a two-layer material twisted at the desired angle. To solve this problem, Pendarkar's team has developed a faster technique for imaging these twisted bilayer materials. They call this technique torsion field microscopy.
We've been successful in developing a technique where within a matter of hours, we can tell what the twist angle is.
To perform torsional force microscopy, you need an atomic force microscope. This is a high-resolution microscope that produces an image by scanning a sharp tip across the surface of a material. As the tip moves up and down the topography of the material, the microscope can produce an image of that surface. The group's innovation was to vibrate the tip of the microscope at a resonant frequency as it's scanned across the sample. You can think of the microscope tip as similar to a pointed end attached to a swimming pool's diving board.
You jump off of the diving board keeps on shaking at a particular frequency.
But unlike a diving board, which vibrates up and down, they vibrate the tip left and right. These resonance frequencies are on the order of megahertz and will change subtly as the tip moves across the material's surface. The microscope can then detect subtler changes on the material's surface by tracking those changes in frequency or amplitude. They demonstrated this method with different configurations of graphene layered with hexagonal boron nitride, which are common single-atom layer materials used in twistronics. The technique works at room temperature in air.
By shaking this tip left to right, it turns out that you're now not just sensitive to topography, but you're actually even more sensitive to local changes in the surface friction.
Sensing the friction and the topography helps to reveal the moiré superlattices. Some standard atomic force microscopes were already outfitted to perform this vibration-based technique, but the manufacturer that developed it had not found an application for it. With this new imaging technique, Pendarkar hopes to improve researchers' ability to quickly determine the structure of twisted bilayer materials.
With this new set of eyes, we can actually rapidly make lots of samples and quickly characterize them in an AFM and say, look, this is the sample that I want.
This work was published in a recent issue of the Proceedings of the National Academy of Sciences. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.